This week, we're going to be talking about chemical quantities and stoichiometry. Now, stoichiometry is a method that allows us to measure the amount of substances involved in chemical reactions and then relate them to one another. We've been doing some stoichiometry throughout the semester so far. Whenever we converted centimeters to inches, or last week converting different air pressures, that is stoichiometry. We're relating them one one measurement to another. We're going to do a little bit more this week involving that and take it one step further and look at stoichiometry in terms of chemical reactions. Now, we have established units for large numbers. We mentioned this at the beginning of the semester again. Like 1 kilometer is used instead of 100,000 centimeters. It's easier to condense numbers, like a dozen, 12. We could go and order 12 dozen cookies from the bakery. We don't walk in and say, I need 144. That is just a large number. But if you say I need 12 dozen, it's easy to see, oh, I can break it up into these groups. So I have 12 groups of 12, and it makes it easier to count and manage. We do this for chemical equations and atoms as well, because atoms are so small that it's it's billions upon billions upon billions of numbers. It's like septillion, I think is what it is, if I actually looked it all up to see, okay, in one, in this little drop of water, we have a septillion atoms. What are you going to do with that? How are you going to manage it? So that we create units to make it more easily managed. Now, why in the world do we even care about stoichiometry? We use principles based off of stoichiometry every day without even realizing it. Airbags are an example. Now, airbags actually use sodium azide to inflate upon impact. The sodium azide will react and create nitrogen gas, and that's what fills the airbag and makes it inflate. It's an extremely rapid, explosive reaction. People have gotten hurt from the airbags. That's why small children aren't supposed to be in front, because with the amount of pressure that it explodes and the position a small child would be in, it could be deadly to the child. So again, chemistry, part of our daily life, it's really important because those engineers have to calculate the amount of sodium azide that we need to start with in order to create enough nitrogen to inflate the airbag. If we know this pressure, again, using our combined gas laws, if we know this pressure and this temperature, how much gas do we need in order to inflate it to this volume? So we're combining what we've learned from last week and the information we learned this week. Engineers combine that in order to calculate how much sodium azide has to be in your car steering wheel in order to ignite and create that nitrogen that you need in order to inflate your airbag. So stoichiometry, very useful. Now, atoms are so tiny that we have a small sample. You're going to have so many atoms that you can't count them. So scientists created a unit of measure that's used to count the numbers of atoms, molecules, or formula units Remember, molecules, these are covalent compounds. Formula units, these are your ionic compounds of a substance. So 1 mole is just like 1 dozen. It's a unit to describe a larger quantity. You have a dozen, you have a gross. 1 gross is 12 dozen, which is 144. So you have different units to describe amounts. You have a ream of paper, for example. And you know that a ream of paper is always the same quantity. 1 mole is always the same quantity. It is 6.02 times 10 to the 23rd atoms, molecules, or formula units in it. This is known as Avogadro's constant. It's not avocado, but if you can remember avocado, you can make that association to Avogadro. Avogadro's number is 6.022 times 10 to the 23rd. Now, a molar mass is the mass of 1 mole of a pure substance, and for atoms, it's the atomic mass found on the periodic table. It's the mass in grams of the average atomic mass for that element. So if we look at the periodic table here, and we look at carbon. Carbon's mass here, this is its average atomic mass. The average atomic mass on this periodic table is at the bottom of each square. And we know that if we have 12.011 grams of carbon, we have 1 mole of carbon, which is also 6.022 times 10 to the 23rd atoms of carbon. If we have 98 grams of technetium, that means we have 1 mole of technetium. And if we have 1 mole of technetium, we have 6.022 times 10 to the 23rd atoms of technetium. If we look at potassium and we have 39.098 grams of potassium, that means we have 1 mole of potassium. So the molar mass is just the mass in 1 mole for that particular atom. So that mass is the mass found on the periodic table. Sodium, 22.990 grams in 1 mole. That's the molar mass. The molar mass of iron, that's your 55.847 grams in 1 mole. Molar mass of copper, this is just off the periodic table, 63.546 grams per mole. And we can use the molar mass to convert grams to moles and then to atoms, because 1 mole equals the molar mass found on the periodic table, which equals 6.02 times 10 to the 23rd atoms or molecules or formula units. No, I can't really write as well on the screen, but this, just so that you see, you can make a conversion just like we did before. 1 mole equals a molar mass from the periodic table, which also equals 6.022 times 10 to the 23rd atoms, molecules, or formula units. Now, if the substance exists as a molecule or a compound, the particles in 1 mole of that substance are composed of atoms. So if we wanted to find the molar mass of water, we would say I have 2 hydrogens. If I look at the periodic table, the molar mass of hydrogen is 1.01. Plus, now I look at my oxygens. I have 1 oxygen. If I look at the periodic table, the molar mass of oxygen is 16.00. So if if you're looking, some decimals go out to the 3, 4, 5 places. It's okay if you just take it to 2 places. So then I'd add that up and I get 18.01 grams per mole is my molar mass for water, H2O. I'm adding up all the individual molar masses to get the total. Now, the molecular mass is just the mass of a covalent compound in atomic mass units. The formula mass, then, remember, the formula units are ionic compounds. Molecular mass, covalent compounds. It's the same process for calculations, it's just a different thing. So what if I say, what's the molecular mass of C2H6O? How would I figure that out? Well, I look and I say, well, I have 2 carbons. If I look on the periodic table, each carbon has a mass of 12.01. Plus, I have 6 hydrogens. Each hydrogen has a mass of 1.01. Plus, I have 1 oxygen. Each oxygen has a mass of 16.00. So I'm going to add that up. 2 times 12.01 plus 6 times 1.01 plus 1 times 16. That gives me 46.08 grams per mole. That's my molar mass of C2H6O. You have to use the periodic table. You're going to struggle if you don't. So here, what's the molar mass of hydrogen? So if I look, again, let's go to our periodic table. Hydrogen, 1.01, because remember I said it's okay if you just take it to 2 decimals. So 1.01. But I have 2 of them. So I look and I say I have 2 hydrogens. And each one has a mass of 1.01. So that gives me molar mass is 2.02 grams per mole for my H2. Now, we know now the molar mass of hydrogen is 2.02 grams per mole. We're going to do the same thing for sodium chloride. Well, we have 1 sodium. Let's look at our periodic table. Sodium has a mass of 22.99. Chlorine has a mass of 35.45. So we have 1 sodium times 22.99 plus 1 chlorine times 35.45. Let's do the math. 1 times 22.99 plus 1 times 35.45. And that gives me 58.44 grams per mole. So 1 mole of sodium chloride is 58.44 grams. Okay, we're going to do another one. What's the molar mass of magnesium hydroxide? Well, let's come look at the periodic table. Magnesium is 24.31. Hydrogen is 1.01 and oxygen is 16.00. Remember, we're just going to 2 decimal places. So we come back. Here I look and I see 1 magnesium, and it's 24.31 grams per mole. Okay, plus, remember this gets distributed in. So we have 2 oxygens times 16.00 plus 2 hydrogens at 1.01. So we add them all up and we get 1 times 24.31 plus 2 times 16 plus 2 times 1.01, and we get 58.33 grams per mole. So 1 mole of magnesium hydroxide has 58.33 grams. All right, let's clear this. Okay, so let's do a practice problem. What's the molar mass or molecular mass of water? I want you to try each one of these and then come back and check your answer with us. So what's the molecular mass of water? Well, we know that we have 2 hydrogens. Each hydrogen has a mass of 1.0 according to what we're given, plus 1 oxygen times 16.00. That gives us 18 grams per mole. That is B right here. C, or 2, says which compound has the greatest molecular mass? So we're going to have to calculate for each. So if I'm going to do CO2 here, I have 1 carbon. If I look at the periodic table, carbon has a mass of 12.01 plus 2 oxygens, which has a mass of 16. So this gives me a mass of 44 grams per mole. Let's look at B now. We have CH4. 1 carbon times 12.01 plus 4 times 1.01, because carbon has a mass of 12, hydrogen has a mass of 1. This gives me a mass of 16. So far, carbon dioxide is the one that has the highest. We have one last one to do, and that is ammonia in C, because D we did up above. So if we look at the periodic table for NH3, we have 1 nitrogen. Each nitrogen has a mass of 14 plus 3 hydrogens, which each have a mass of 1. So this gives us a mass of 17. So carbon dioxide, A, gives us the greatest molecular mass. So let's look at the molar mass of glucose. We're given the elements here, their mass. So we don't have to go to the periodic table and look those up, which is helpful. So we have 6 carbons, each has a mass of 12. Then we have 12 hydrogens, each has a mass of 1, plus 6 oxygens, each has a mass of 16. So we add those up, and 6 times 12 plus 12 times 1 plus 6 times 16. and we get 180 grams per mole. So the mass of glucose is C, 180 grams per mole. Now let's look at molar conversions. Now that we know how to calculate molar mass, we can actually go through and calculate how many moles of something we actually have. So if we have the mass of an iron bar is 16.8 grams. So remember where I talked about what are you given? And then what do you need to find? So we're given 16.8 grams. We want to know how many iron moles are in the sample. So we say, well, I'm given 6.8 grams of iron. I write that down. Then I want to know how many moles. So moles will go on top, moles of Fe, and grams of iron will go on the bottom. Now this is where we need to look at the periodic table. And we go to the periodic table, find the mass of iron, 55.845. One mole has 55.845 grams of iron in it. So now, if I want to know how many moles are in 6.8 grams, it's 6.8 times 1 divided by 55.845. My grams have canceled out. So that gives me 0.301 moles of Fe. I could even calculate how many atoms of iron I have if I wanted to, just with that information. So what if I wanted to determine how many moles are there in 18 grams of hydrogen? And it says, remember, hydrogen is diatomic. So that means we have H2. So I have to determine this molar mass. So I look and I say, well, hydrogen has a mass of 1, and I have 2 hydrogens. So the molar mass of hydrogen is 2.01 grams per mole. So I start with what I'm given, which is 18 times, I need to turn it into moles. So moles go on top. My molar mass goes on the bottom. And that would be 2.01 grams per mole. But I don't have to do the mole part because that's where that's coming in. Because we know with the molar mass that there are 2.01 grams for every 1 mole. So that's why we write it that way, with the 1 mole over the grams. So this way we can cancel out the grams. So it's 18 times 1 divided by 2.02, and that gives us 8.9 moles of H2. I want you to make sure you have both the unit and the element or molecule there, because when we take this farther, you're going to need to make sure that you keep the units and identity of the molecule or substance with it. Okay, let's look at this next one. How many moles are there in 15 grams of silver? All right, so what are we given? We're given 15 grams of silver. What do we want to turn it into? Moles of silver. What we want always goes on top. What we want to get rid of always goes on the bottom. If we look at the periodic table, the molar mass of silver is 1.787. So 1 mole of silver has a mass of 107.87. That's 15 times 1 divided by 107.87. That gives us 0.14 moles of silver. All right, let's go back to this last question that we did. We were given a mass of an iron bar and that it was 16.8 grams. This time, instead of asking how many moles or how many moles there are, we want to know how many atoms there are. So we already know from a previous problem that we have 0.301 moles. So we can go from grams of something to moles by using 1 mole over the molar mass. And that'll give us a number of moles. So that's kind of a basic equation for determining moles. But now we want to know how many atoms there are. Well, we know that 1 mole equals 6.02 times 10 to the 23rd atoms, or molecules, or formulas, depending on what you're asking. So 1 mole equals 6.02 times 10 to the 23rd something. All right, so we know that. If I have the number of moles now, so I'm going to start with my moles, 3.301 moles of Fe. I can go from moles to atoms using these two numbers. This is just like what you did with the money. How many dollars is 12 dimes? Well, I know 10 dimes equals $1, and you do the math automatically. It's the same process, you just have to think about it a little bit more. What do I want? I want atoms, so it's going to go on top. What do I want to get rid of? I want to get rid of moles. And it's moles of Fe and atoms of Fe. I know that 1 mole is equal to 6.02 times 10 to the 23rd atoms. So now I could put this in 0.301 times 6.02 times 10 to the 23rd. That equals 1.81 times 10 to the 23rd atoms of iron. I have to use the units that I still have that haven't been canceled out. Then here is the work in a more clear fashion, if it makes it easier for you to follow. 0.301 moles times 6.02 times 10 to the 23rd atoms per 1 mole equals 1.81 times 10 to the 23rd atoms of iron. Okay, we're back to this problem. If we have 500 grams of C2H6O, how many molecules is this? So we have 500 grams. We want to go to molecules. We can't go straight from grams to molecules. We have to go from grams to moles and then molecules. It's like if you're in a room and you want to go from room A to room B, you can't just walk through the wall. You have to have a door. So, in this case, the moles is a doorway. In order to go from A to B, you have to go through the door. In order to go from grams to molecules or atoms, you have to go through the door, which is moles. This is your door. These are the two rooms. In order to go from grams to molecules, you got to walk through the doorway. We're not X-Men. We can't walk through the walls. So we have to go through the doors. We got to take that extra step. So we can't go straight from grams to molecules. First, remember, we go from grams to moles by using your molar mass. So we know that 1 mole is equal to your molar mass. And that will give you moles. So back to this. In order to find moles first, so that we can get to molecules, we have to calculate our molar mass. So we have 2 carbons. Each carbon has a mass of 12.01 plus 6 hydrogens, which has a mass of 1.01, plus 1 oxygen, which has a mass of 16. So let's add that up. 2 times 12.01 plus 6 times 6.01, or times 1.01 plus 1 times 16. So that gives us 46.08 grams per mole. So in 1 mole, we have 46.08 grams. So since I want to cancel out grams, grams has to go on the bottom. Mole has to go on top. So we have 1 mole and 46.08 grams. Grams will cancel out. This is C2H6O. So it's 500 times 1 divided by 46.08. That gives us 10.9 moles of C2H6O. That's the first step. Now, if we look at this, we are in the doorway. We're right here. We're with our moles. Now we can walk out of the doorway into our molecules room now. So I take my moles, 10.9 moles of C2H6O, and now I can find molecules. I know 1 molecule is equal to 6.02 times 10 to the 23rd. Sorry, 1 mole is equal to, there we go. 1 mole is equal to 6.02 times 10 to the 23rd molecules. What do I want to turn it into? I want to turn it into molecules. So molecules go here on top. What do I want to cancel out? I want to cancel out my moles. So moles go on the bottom. I look here. I know 1 mole is equal to 6.02 times 10 to the 23rd. My moles cancel out. And this is 10.9 times 6.02 times 10 to the 23rd divided by 1. And that gives us an answer of 6.56 times 10 to the 24th molecules of C2H6O. So you can see why we use the unit of mole, because these are really big numbers. It helps us to see just how tiny atoms are whenever we put it in this perspective. Here is a neater version so that you can follow along and see. You can see this thought process when I write it out here. It's all nice and neat, keeping it together for you. Okay, we're going to stop there for now. I hope you guys have a wonderful week. Practice, 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 and we'll do more whenever we come back.